and welcome to Allen High School's discussion of acids and bases. We were in the midst of talking about properties of acids and bases and some of the terminology involved. We had just talked about amphiprotic or amphoteric substances. Amphiprotic, amphoteric, depending on where you're reading, are substances that can act as an acid or a base depending on what the other substance is. Now, the next subject I want to talk about, or the next concept, are polyprotic. Poly means many, protic means protons. So these are acids that have the potential to give more than one proton away. Now, when we write these, we typically lose one H plus at a time. So we would do a sequence of steps. So let's take a look. HCl is not polyprotic because it doesn't have more than one. It has just one H plus. H2S is. It has two. HClO3 is not. It only has one. Let me show you what I mean by writing sequential dissociations. So we have H2CO3. It is not one of your strong acids, so we will use a double arrow. We're going to lose one H plus at a time. So we take away one H and one plus charge, and we get HCO3 minus. Now then that HCO3 minus can go on to act as another acid. I'd lose the second H plus, and I'd get CO3 2 minus. Now, when you have polyprotic substances, that middle substance is amphoteric. Do you notice that in this direction, HCO3 minus is acting as a base? In this direction, it's acting as an acid. So it is amphoteric. All right, so the multi-steps, this is phosphoric acid. It's kind of an awkward way to do it because it's adding H pluses across. I personally would have done it this way. We have H3PO4. That is weak, so we're going to lose an H plus, and we'd have HP2PO4 with a minus. The minus plus the plus gives that, the neutral. Then that H2PO4 can go on, since this is polyprotic, and lose a second H plus. And now it'd be minus 2, plus 1 minus 2 gives you the minus 1 on the reactant side. All right. And then that can go on, and HPO4 minus 2, or 2 negative, can lose yet another. So this polyprotic acid would be called triprotic. Sorry, that was a little messy there. 3 protons. A triprotic acid. Carbonic acid would be considered diprotic. All right. The in-between substances for each of these are amphoteric. That can act as an acid, giving up a proton, which it did here, or it can act as a base, which is what is happening in the reverse reaction here. And then this is a second in between, and that too is amphoteric because it's acting as an acid here. It gave up an H plus, but in the reverse of that part, it's acting as a base. So the in-between charged species of a polyprotic are considered amphoteric. All right, let's take a look. You've already seen me do this. I've really written a couple already of dissociation reactions. This is a bit of a review to tie things together. Remember that strong acids and bases dissociate 100%. And to show that, we show a single arrow indicating they dissociate 100%. Weak acids and bases dissociate less than 100%. All right, and we would do a double arrow. Okay. Now, if we had a strong acid of 0.1 molar and a weak acid of 0.1 molar, okay, the pH of the strong is going to be greater than the weak. Now, we can really only compare that if they are the same concentration. You can actually have a very concentrated weak acid that can get pretty darn low. So we got to be careful with that comparison. We really only want to be comparing those pHs when we have the same concentration. So the pH, let me rephrase that, the pH of a 0.1 molar strong is going to be greater than a 0.1 molar weak. So as long as they're the same molarity, we can make broad generalizations like that. Memorize, memorize, memorize. You have to know these. All right. Now, I want to give you a clue on these oxyacids. If you're really in a bind and you forget, if you take your number of H pluses, multiply it by 2, and if that is still less than your number of oxygens, then it's likely to be strong. It's not going to work all the time, but it works pretty well. So nitrogen has 1 hydrogen times 2 is 2, which is still less than the 3 oxygens. Okay, so these are the weak ones you have to memorize. Strong bases, group 1, group 2 hydroxides except beryllium and magnesium. So memorize, memorize, memorize. All right, strong acids and bases are strong conductors of electricity because they go 100% to their ions. Weak acids and bases, like an example of a weak base would be that CH3NH2 is weak. They are weak conductors of electricity because they dissociate less than 100%, which means that a good portion stays as an uncharged species, and we need ions to provide a pathway for electrons. Those ions provide, you can think of them as a stepping stone. They're a pathway for electron movement. So weak give us many fewer ions, so the pathway isn't as clean cut, so it's less. All right, let's write the dissociation reaction. First, you want to identify it. We're memorizing that as strong. We're memorizing that as weak, and we're memorizing this as weak. Now, this one's probably getting up there. I'd have to look up some values on it, but we're going to call it weak. That's what the AP does. They give you a group to memorize as strong, and then you assume all else is weak unless there's other indications to help you out some more. All right? So HClO3, I'll dissociate this one without water. We'll go 100% single arrow to H plus ClO3 minus. Okay? Now, let me do the next one with water just to give you an indication of what we have here. So if I included water, this is going to be assumed to be weak, absent of any other information, and its acids donate the H plus, so the H plus is going to go on to the water, which would give you H3O plus. It's just a lot more to write. I know it sounds petty, but most people are going to do it this way. Although I've noticed more and more books are getting a little bit more particular about writing it the proper way, the way it truly exists in solution. All right, acetic acid is also weak, and it's the H on the front that's acidic. These 3 H's in the middle, right here, they don't come off. These H's right there are not acidic H's. Don't take them off. It's just the one in front. And so I get C2H3O2 minus plus H plus. Notice I defaulted right back to the cheaty way. All right. Let's identify, this is strong, weak, and weak. I never put water with my strong. It can get rather confusing, to be honest with you. So I'm never going to put it with my strong, and I have to put it with my weak. So that would give me barium plus 2 hydroxides. And I bet you can guess that since we have a mole ratio here, we're going to hit on some stoichiometry soon. Now, weak has to have water. You can't be lazy like we are up here, because a base is stealing a proton. So you have to provide it with something to yank a proton from. So you have to show the water. Must show water on weak bases. So the base is going to steal a proton. Remember, I told you earlier that that proton goes on to the nitrogen portion of the molecule. I added an H and a plus charge, and then that left me with OH minus. Okay, let's try this triethyl. This is trimethylamine. The CH3 is meth. Remember, 1 carbon is a meth group. Remember, meth eats people's brains. 1 carbon is a meth group. So I've got CH3, 3. There's 3 of them around that nitrogen. So we'd have nitrogen, it'd have 3 methyl groups and the non-bonded pair of electrons. So 3 groups on it like that, and the non-bonded electrons. Now, that's where we can pop that H plus on. That's why the H goes on the nitrogen end. So then I'd have NH, got a little bit ahead of myself. So that's the base. You must add water or you won't get this right. There won't be anywhere to get an H plus. You have to steal the H and the plus from something. So we'd have CH3, 3, and remember the new H goes on the end there, and we added a plus charge, and that leaves us with OH minus, characteristic of a basic solution. Okay, so that's how we write our reactions. Hopefully you're getting a good handle on that. You're wrapping your mind around that. We are about ready to jump into stoichiometry again. And you know what? You rock at stoichiometry. I just know that we're going to do a great job on that. And I'm going to use our start, shift, stop method. So until then, you know who it is, saying I love ya. Talk to you later.